So it is my pleasure to introduce Ángela Capel Cuevas, a rising leader in quantum information theory and mathematical physics. So currently she's an assistant professor at the University of Cambridge, but held prestigious positions across Europe before, including a junior professorship at the University of Tübingen and a postdoctoral fellowship at the Munich Center for Quantum Science and Technology. Her research has significantly advanced our understanding of quantum Markov semigroups, quantum entropies, and the thermalization of many-body systems. She's the recipient of several accolades, including the Vicente Casellas Prize and the Forbes 30 Under 30 recognition. Ángela is not only a prolific scholar with over 30 publications and invited talks at leading conferences, but also an active mentor and advocate for diversity in science. So please join me in welcoming Ángela Capel Cuevas for today's talk that will be titled The Many Phases of Quantum Entropy, from Divergence Measures to Conditional Independence. Okay, so the spot is yours.
Thank you very much, Francesco, for this very kind introduction. Thank you very much for the invitation to give this colloquium today. It's great to be with all of you, and I hope that I can convey some of the things about quantum entropies that made me be passionate about them. And well, I can convince you why this field is so fascinating. Today we're going to talk about quantum entropies and about different aspects related to quantum entropies. And we will range from their interpretation and their extensions to different divergence measures, and to the study of conditional independence in quantum systems, in particular in 1D. So to start, let me begin by recalling a little bit about the meaning of classical and quantum entropies and how to define them and the properties of these quantities. The first thing that I will do is discuss what what entropy is, and we will go from classical to quantum information. And in a very, very wide way, what we can say is that entropy quantifies uncertainty or information content in a system. And if we study entropy in classical systems, in classical information theory, what happens is that it measures the average information per message that we have. And it is crucial, for example, for some applications like data compression, transmission, and cryptography. And in particular, the canonical measure of entropy that we have for isolated systems, or for particular systems X, which in this particular case is a random variable. We have the Shannon entropy, which is defined by this quantity here. So we have a probability distribution, a discrete probability distribution that is finite, that is composed by these elements Px. So all of them range between 0 and 1, and all of them sum up to 1. And then the Shannon entropy is defined by this quantity, so minus the sum of all the Px's and log of Px. So this is in a very, very simplified way what happens in classical information theory. And now if we want to look at this in the field of quantum information theory, what happens is that analogously we can say that in quantum information theory, entropy accounts for quantum superposition and entanglement, so for this kind of quantum phenomena that characterizes quantum systems. And it is actually central for the fields of quantum communication, computation, and thermodynamics, among many, many others. And now, if we want to take the straightforward analog from the Shannon entropy in the quantum case, this is the von Neumann entropy, and this is defined by the definition that I'm writing here, where now I'm taking rho just as a density matrix. So now I'm assuming for the moment that we have finite dimensional systems and everything. And rho is a density matrix, so it's a positive semi-definite matrix with trace 1. And then the von Neumann entropy is just defined by minus the trace of a certain state rho and log of that state rho. Okay. And why do we care about this kind of quantities? Well, for many, many reasons, but in particular, because the entropy sets the limits on how efficiently we can store, transmit, and hide information, which is something that is crucial for understanding better what happens in information theory, both in classical and quantum information theory. And apart from that, it helps us understand correlations, irreversibility, and complexity in both classical and quantum worlds, which is something that we will be exploring now. Okay, so this was like the very brief introduction. But now if we want to enlarge a little bit more what happens in the classical world, what happens is that if we consider the Shannon entropy, which is the foundational measure of uncertainty in a discrete random variable, this was introduced by Shannon in 1948. And many of the properties that this quantity satisfies are listed here. So the first one of them is that this quantity is always non-negative. The maximum value that it takes happens when all the elements in which it's evaluated, so all the elements of this discrete probability distribution are actually the same, so 1 over n if there are n elements, and in that particular case the value is log of n. And the minimum value happens when we have certainty about this distribution. So we know that there's one value that takes probability 1 and all the others take probability 0, and then the entropy in that particular case is just 0. So it always ranges between 0 and log of n. And the interpretations and applications that we can have for this quantity are very diverse, but in particular, we can interpret it as the average number of bits needed for to encode the outcomes of the random variable x. It can also be seen as the optimal rate for lossless compression, and it's used in many, many fields like statistical mechanics, machine learning, and cryptography, etc. So now, what we want to do is not only take the Shannon entropy, but extend it to other quantities that appear also in the classical literature, and see later what we can do with them in the quantum world. And in particular, if we look at the Shannon entropy, this is a quantity that, as I said, has many interesting operational interpretations and operational applications. But Renyi introduced another family that now is known as Renyi entropies, which is given by this expression here. And the interesting thing that they satisfy is that they are introduced for every alpha that is different from 1, and when you take the limit with alpha tending to 1, you actually get back the Shannon entropy, which means that this is a family that is generalizing the Shannon entropy, so it's extending it in a sense. And this gives you much more freedom to do operations, because now you have a whole family indexed in this parameter alpha that is sometimes easier to work with because of the definition that we have here. And it's actually something that if you prove for these quantities for alpha close to 1, then you can take the limit and by continuity obtain the same information for the Shannon entropy. So it's something that operationally is very, very useful. But some things that we also want to do in information theory is not only take the entropy of one specific variable, but also compare. So in particular, sometimes we want to see how distinguishable two distributions are. And for that, we have to consider something that is called the Kullback-Leibler divergence, which measures exactly the difference between two distributions. And it's given by the expression that I have here. So now this is the sum of the values of the probability distribution P and the values of the probability distribution Q. So now we have the sum of Px and log of the quotients of all these Px over Qx. And in particular, something that we can also do now is study the mutual information, which is share information between variables. So we can study what happens if we have a variable x and a variable y, and how the information appears between these variables. So for that, what we do is take the sum of the Shannon entropies of x and y separated, and then we take the Shannon entropy of both variables at the same time, so this h of xy. This is how we can study the mutual information between the variables. And finally, in the same way that we introduce Renyi entropies as a generalization of the Shannon entropy, we can do something similar now, but for the Kullback-Leibler divergence. And we can introduce something that is called Renyi divergences, which also measures the shared information between variables. And the difference between two distributions, this is a typo. And what happens is, again, that if we take now the limit with alpha tending to 1, we recover here the Kullback-Leibler divergence. So again, this is a family of quantities that extends the Kullback-Leibler divergence. So this was like a very, very brief overview in classical information theory, because now we want to extend this to the quantum world. So the first question is, how can we extend all these quantities quantumly? And in the case in which we only have one random variable or one specific probability distribution, this is very easy to do. And the reason for that is the following. In the quantum world, we want to work with density matrices, and density matrices are going to be positive semi-definite matrices with trace 1, which in particular means that if we look at the eigenvalues of these matrices, these eigenvalues are actually like the probability distribution that we were seeing here. So they are all values that are ranging between 0 and 1, and all of them sum up to 1. So what happens is that now if we look at this matrix and we place in the diagonal of the matrix all the values that are the eigenvalues of this matrix, essentially it's like having all the elements of the probability distributions that we had here. So that means that if we defined now this quantity that we call von Neumann entropy in terms of the eigenvalues of the matrix rho, and we define it exactly analogously to the Shannon entropy that we had here, This allows us to define the von Neumann entropy directly from the matrix row. So not only from the eigenvalues, but from the matrix row in this form as minus the trace of rho log of rho. And the reason for that is that this expression is invariant under unitaries, which means that, of course, if we diagonalize the matrix row so that we have the eigenvalues in the diagonal, then these expressions are exactly the same. So this is why the extension to the quantum world from the Shannon entropy to the von Neumann entropy is totally straightforward. And exactly following the same reasoning, the extension from Rényi entropies to quantum Rényi entropies is totally straightforward, exactly for the same. Because again, we could diagonalize this quantity that appears here, this row to the alpha, and just get back all the eigenvalues of our matrix row, now to the power of alpha. So this is how we will recover the Rényi entropies back. So this seems pretty easy at the moment, but of course, the field of quantum information theory, and in particular, everything related to quantum entropies wouldn't be so complicated if everything could be extended in such a simple way. So what happens now is that if we take a look at some other quantities, the situation gets much more complicated. If we just look at the mutual information as we were defining it only as a combination of von Neumann entropies, we still have exactly the same, because of course, we can just define the extension of each of these Shannon entropies to the corresponding von Neumann entropy, where now A and B are denoting different systems, so we will see geometrically later what this means. And here, this is still pretty straightforward. However, what we will see now is that if instead of defining it as a combination of Shannon entropies, we define it as a combination of relative entropies, this gets much more complicated. And the reason for that is exactly what I was saying. So now, if you tried to define a quantum analog for this quantity in terms of the distance, in a sense, between two density matrices, you would have to create an expression that reduces to this expression in the particular case in which your matrices are diagonal. However, now these matrices can be diagonalized in many different bases. And what this is telling us in particular is that there are too many ways to define this quantity quantumly. In particular, there are infinitely many ways of defining this quantity quantumly. And exactly the same thing happens for Rényi divergences. So we cannot directly have here an expression that automatically extends this to the quantum world. We have to explore this much more carefully. And this is what we are going to do now. We are going to start with the Kullback-Leiber divergence because it's a bit simpler. And if we start with the Kullback-Leiber divergence, what we have is the following. So first of all, from now on, every time that I talk about H and K, they are going to be finite dimensional Hilbert spaces. And rho and sigma are just going to be density matrices that I'm denoting by this in these finite dimensional Hilbert spaces. So they are just, again, positive semi-definite matrices with trace 1. So what happens now is that if we look at this expression, we have the log of the quotient of each of the terms px over qx, which in a sense could be seen as, well, if we separate this quotient, it could be seen as the difference of the logs, no? So it could be seen as the log of px minus log of qx. So if we try to automatically extend this to the quantum notation, so to the quantum framework, we could create something that can be written in this form. And this is called the omega k relative entropy, and it's given by this expression, no? But it's the trace of the first element, which is the analog of what appears here. So now it's not P, but it's rho. And then the difference between the logs. So the difference between the log of rho minus log of sigma. And of course, these quantities are not the same, but what happens now is that if rho and sigma diagonalize in exactly the same basis, then you see that this quantity is exactly the same as this one, where these elements would be the eigenvalues of these corresponding matrices. And this definition that I'm using here, I'm being a bit sloppy in the notation, so this definition is only valid whenever the kernel of this density matrix is contained in the kernel of this density matrix. Otherwise, we would be kind of dividing by 0, so this wouldn't be well defined. So in that particular case, what we do is set this quantity to infinity. So here I'm just assuming that the kernel of this is contained in the kernel of this. However, as I said, there are infinitely many ways of extending this to the quantum world. And well, we just took this because, well, it's from the visual point of view, it's kind of straightforward, and it's operationally a very interesting quantity. It has many different interpretations, and it's very useful for many applications in quantum information theory and in other fields. So of course, everybody's very familiar with this quantity, and it appears in many different settings. However, another quantity that is also getting some attraction in the past few years is something that is called the Belafkin-Stashevsky relative entropy. So I will call it BS entropy during the rest of the talk because of Belafkin and Stashevsky. And this quantity is another way to invert the state that would appear here with respect to the state that would appear here. So it would be another way to write this quotient, so to say. And of course, since we are taking a log of a matrix, we need that this matrix is a positive semi-definite, which is something that we are managing by having rho 1/2, sigma minus 1, and rho 1/2. So it's just a way to write this quotient again. And of course, we also have in front of it trace of rho. So again, you can see that if rho and sigma are diagonal, so if both of them diagonalize in the same basis, then this quantity also reduces to this same quantity, to this same Kullback-Leibler divergence. So these are two possible extensions. There are many more ways to do that, but these are, in a sense, two extremal definitions. So what always happens here is that we have this relation between the omega k relative entropy and the Belafkin-Stashevsky relative entropy. This is always an upper bound for the omega k, and they coincide if and only if the two states commute. So if and only if rho and sigma commute. So essentially, they coincide if and only if we have the classical case. Which means that in general, whenever you have any quantumness, this is very interesting because these two quantities really produce something that is totally different. And this is going to give us many, many interesting different applications for them. But again, there are in principle infinitely many ways of extending this quantity. So in principle, one could construct a whole path of entropies between both of them. And this is something that in particular has been explored in this recent paper, in which the idea is that the authors interpolated between these two quantities to construct many, many more. The expressions that they obtain are not very explicit, so I don't want to write them here because this will get too messy. But the idea is essentially that somehow you can create many quantities between them, and these quantities also have very interesting applications. So you can, in principle, define many quantities satisfying the right properties so that they extend the Kullback-Leibler divergence. However, I must say that only these two have been explored and really explored in the quantum literature.
Sorry,
Okay, so
is
now
it okay to ask a question now?
Of course, yes, I'm very happy to take questions now.
Is there any case where omega relative entropy becomes zero, but this BS entropy is still like positive?
That's a very good question. No, because this quantity is zero if and only if rho equals sigma. So this is something that can be proven. It is zero if and only if rho equals sigma. And for this quantity, this exactly the same thing happens. That this is zero if and only if rho equals sigma.
So like, is it possible to lower bound like omega k relative entropy by the multiple this BS relative entropy, or is it, no?
That's a very good question. So you can do that. We will say that. So you can do that, but paying a price, of course. So you have to
Okay.
pay some prefactor because otherwise, I mean, you would violate this inequality that we have here. You can do that, but we will see later that when you actually add some other terms, it's impossible. So when
Thank
you
you.
have some different steps, but yeah, it's a very nice question. Thanks.
May I also ask a small question?
Yes.
So in classical information theory, I'm trying to see if there's a relationship to Chensov's theorem, right, which says like there's a unique information metric on the space of states. And in quantum theory, like there's a whole family of information metrics coming from like matrix monotone functions. And I'm curious if there's like an analogy here between classical relative entropies and quantum relative entropies where you have this whole family that might have geometric origins. Do you know if you have any thoughts on that?
I don't, I mean, I could imagine that something very similar happens, no? Because exactly because of what you're saying, because you have this extension, no, from the classical to the quantum, in which you have many, many more definitions for kind of extending the same behavior. But I don't see from the top of my head how to connect the two things directly. But I could imagine that there's
Okay.
some relation, yes.
Gotcha. Thank you.
Yeah, thanks. Wait, so once we have these fundamental quantities that we are going to be exploring in the quantum case, What we are going to do now is review one of their fundamental properties, which is actually something that we are imposing so that these quantities are valid for us in a sense. And this quantity, this property is called data processing inequality. And the idea now is that we are going to consider relative entropies together with something that is called a quantum channel. A quantum channel is just a linear map that satisfies, well, it goes from the state of density matrices in the finite dimensional Hilbert space H to the one in K, such that these maps are trace preserving. So when you take the trace of T of rho for any state rho, this is the same as the trace of rho. So the trace doesn't change. And the map is positive, which means that it brings positive semi-definite states to positive semi-definite states. And not only that, but it's also completely positive, which means that every time that you tensorize your map T with an identity in any dimension, so with an identity map in any dimension for any n, going from 1 to infinity, then this map also has to be positive. So when we have all these properties here, we call this map a completely positive and trace-preserving map, and this is what it's usually called a quantum channel. And this is the fundamental object to study how to transmit information in quantum information systems. So considering quantum channels, what happens now is that if we look at the relative entropy, initially at the omega k relative entropy, we know that applying a quantum channel in a relative entropy, so applying it in both inputs rho and sigma, cannot increase the information that we have there. So it cannot increase the distinguishability between rho and sigma. The other way around, we always have a lower bound for the initial relative entropy in terms of the relative entropy after the application of the channel. This is something that always holds. And this is a very fundamental property that we need to impose every time that we define a relative entropy or a divergence, as we will see later. But sometimes what happens is that you don't lose any information at all. So sometimes you actually have in this data processing inequality an equality condition. So essentially you have an equality between the expressions before and after applying the quantum channel. And this is a situation that was explored by Betts in the 78. And he proved in particular that this happens if and only if the state rho, so the first one of them, can be recovered in terms of the other one, so in terms of sigma, by this expression here. And this expression is now known as the Betts recovery map. So this expression, what it's doing is taking the T of rho that we have here and placing it in the middle. And then it's conjugating it with the T of sigma from the left side and from the right side. So now we have T of sigma to the minus 1/2 and T of sigma to the minus 1/2. And now it's taking the dual of this map T. So now this is the T star of everything. So it's applying to all this expression here. And it's conjugating this expression with the sigma 1/2 and the sigma 1/2 that we have here. So this is why this is a way to invert the application of the channel T with respect to the value sigma that we are using here. And what he showed is that if you have a rho, if you have this expression being satisfied for state rho, then this is an equivalence to not losing any information when applying the channel. So now what I will do from now on is denote this by this recovery map R sub T super sigma, because I'm essentially saying that I'm recovering the channel T with respect to the state sigma, composed with the application of the state of the channel T to the state rho. So this is how I will denote this expression from now on. And the reason why I'm separating this map from this map is because I want this to be a quantum channel. And if I introduce the application of this T already in the definition of this, then this is not a quantum channel anymore. So this is essentially why we separate these two parts here, so that we actually see that we apply T to rho and then we recover it. We recover rho from this. Okay, so this is something that has been well known for many, many years in the community for the omega k relative entropy. However, we can also look at what happens for this other quantity that I was mentioning for the BS entropy, and exactly the same thing happens. So we also have the data processing inequality, because this is why this quantity is interesting for us. And we can also explore the equality conditions. And this is something that we did a few years ago with a collaborator, with Andreas Blum. And we actually observed that you obtain a very, very similar expression and a very similar interpretation. So you also have the situation that you don't lose any information after applying a quantum channel T, if and only if you can recover rho, but now by this expression here. And this expression, if you look at it carefully, it's really the analogous one to the one that I had here, but it's totally symmetric. So it's symmetric version. It's asymmetric version, sorry. So you have now T of rho, which is this term here, and now you reconjugate it with T of sigma to the -1, but now only from the one side, so only from the left side, for example, which is here we have -1/2 and -1/2, and here we have everything on the left side. And now we also have this T star of everything, and now we also conjugate it with sigma, but only from the left side again, so instead of having left and right. And this expression, it's very nice for some reasons and very bad for some others. So the nice part is that, well, it only involves like 3 different states. If you forget about the T star for a second, and here it involves 5. So computationally, it's easier to do, and it also doesn't involve square roots, which are sometimes a bit problematic. However, obviously, it's very problematic from the point of view of operations in quantum information, because this map B that I'm writing here is trace preserving, but it's not completely positive, and not only that, it's not even positive. So we have now a linear map that is trace preserving, but it is not positive whatsoever. So this means that well, it's very problematic for certain applications we could try to conceive from here. So this is one thing that we will keep exploring now in the next slides. But what happens also in the quantum community, very frequently in the quantum information community, is that when we want to understand these quantities, what we can do is look at a particular case that is a bit simpler and see what happens there. And the particular case that we are going to explore is that of tripartite Hilbert spaces, in which we have now our state rho being a tripartite state in this tripartite space, but our state sigma is actually going to depend on rho. So it's going to be a marginal of rho in BC, so tracing out A, and reconstructing it with the identity normalized in A, which means that this is really totally dependent on rho. So we are now comparing 2 states that are very alike in a sense. So when we take now this equality condition and this relative entropy and this equality condition for this quantity, this can actually be rewritten in the following form. So if we now replace here rho ABC and sigma being of this form, and now we replace here T of rho ABC, which is taking the partial trace in C, so it would be rho in AB, and here this would just be rho B. What we actually obtain is a quantity that is called the conditional mutual information. So we obtain 4 different terms here, which are actually 4 von Neumann entropies. So we have the von Neumann entropy in AB, so in these 2 systems, the von Neumann entropy in BC, and then minus the von Neumann entropy in ABC, and minus the von Neumann entropy in B, in the middle system. So this is why this is telling us the mutual information that we have between systems A and C conditioned to B. So this is why this is called conditional mutual information. And the nice thing of all these quantities that we have introduced until now is that this quantity, this conditional mutual information, can be rewritten in several forms. So using this expression here, and using all these terms, it's very easy to see that this can be rewritten as a difference of 2 relative entropies, where we have the states rho ABC and identity in A over dA tensor rho BC and all these marginals here. But it can also be written by replacing these 2 terms by rho A, by the marginal of our state rho ABC in A. So we have these 3 equivalent definitions, and they are all the same. And what we know now is that if we explore conditions in which these 2 terms are equal, this is equivalent to just exploring when this conditional mutual information vanishes, so when this is equal to 0. And this happens if and only if we can simplify the very large expression that we have here to this very simple expression. So it happens if and only if rho ABC can be written in this form. So we have rho AB in the middle, we conjugate with rho B to the -1/2 on both sides, and then we conjugate to rho BC 1/2. And this is very, very nice. But, well, this is very well known for the relative entropy case. But then we can wonder, what happens now for the Belafkin-Stachewski relative entropy? And the situation gets much more complicated. And the reason is the following. The reason is that here we have 3 equivalent definitions that were exactly the same. But in the BS entropy, if we extend these definitions, we get totally different quantities. So in principle, all these quantities are totally different and have totally different properties. So we define them in different forms. This one, we call it one-sided BS conditional mutual information. And this one, we call it two-sided BS conditional mutual information, just one, because this one doesn't have, and only has some trivial state in the part A, and this one doesn't have this trivial state in the part A. And what happens is that even though these quantities are totally different and in principle are not comparable, they actually reduce to the same recovery condition when all of them are zero. So when all these BS CMIs vanish, we always have that this happens if and only if we have the analog of the expression, that we had before. So before we had that there was equality for the BS entropy if and only if it could be recovered in this form. And now if you translate this to this setting, we actually have that rho ABC equals rho BC. So this should be rho B minus 1, there's a typo here, and then rho ABC. Okay, so this is exactly how we define now this recovery condition in this asymmetric framework. Okay, so from here, what we can do now is talk about...
Sorry, can I ask a question?
Yes, definitely.
Is this if and only if relation robust under the like small errors?
That's exactly what I'm going to say in the next slide.
Okay. Okay, great. Thanks.
Yeah, very good intuition. Yes, thanks. So
May
what
I
happens
also
now?
ask?
So
Oh,
yes,
can I ask a question as well?
yes.
So do you have an so one thing that seems a little bit strange to me is that the Belavkin-Stavetsky relative entropy is defined in terms of, conjugating with these square roots, but then these equivalent conditions for when it is zero do not involve square roots,
Yes.
right? Conjugating with square. But on the other hand, right, with the Umagaki relative entropy, it doesn't involve square roots in the definition of the relative entropy. But however, this characterization for when the channel, preserves this quantity involves the square root. So there seems to be like a mirror, like an asymmetry here in terms of like where the conjugation with square roots are appearing. So do you have is there some sort of like intuition behind that?
So the intuition will be a bit complicated to say. It actually comes from the proofs in a sense, no? So what we did
Comes from what? Sorry, I didn't hear you.
From the proofs of the results. So what we did to prove this result, and the more general version of it, was essentially follow the proof of Betz for the original result for the relative entropy. And what happens there is that you write the difference between these two quantities in terms of you have two logs, right? So even in the case of the relative entropy, you have a log. You can write this as the log of the modular relative operator between rho and sigma. And here you have a log of just this product of matrices. And what you do is consider this quantity before and after applying the channel as the difference of two logs, and then the same thing here. And then in this case, you have, in both cases, what you do is write the integral representation of the logarithm, of the matrix logarithm. And then you simplify terms. And then what you have is essentially a collection of slices. And with all these slices, you see when they vanish, no? And seeing when all these slices vanish is exactly when this quantity vanishes. And also the same thing for this quantity. And funnily enough, because of having the relative modular operator here, or this product here, this is what gives you actually in this slices being equal to zero expression, here the square roots and here the non-square roots. So it's a bit strange. It's really coming it's an artifact of the proof, no? But I agree with you that this is kind of a funny thing.
Okay, thanks.
Thank you.
I should make a comment just because James asked this question and I think it's relevant, but both of these maps that you're written here are examples of recovery maps, at least when you restrict to the set of states that still end up going to states, right? Here, like your rho ABC happens to be a state when you apply this non-completely positive channel to your state in order to recover the state. So it's taking some states and pushing them forward to other states as well, right? I was actually going to ask about in this case, rho ABC happens to be a state when you apply this B map to T of rho. But if you apply the B map to other states, you don't get necessarily a density matrix, you get something else, right?
So that's exactly the problem, right? I mean, if you apply it to something that is already in this form, then yes, I agree with you, then it still outputs a density matrix, no? If you apply it to anything that you have zero information about, then you have no idea what this is. But in general, this is definitely not a state, exactly. That's a very good point, yes. Yeah, thanks. Yeah, so going back to the question that was asked like a second ago, what happens now is that, of course, we have a collection of, we have several relations between exact conditions. So we have exact saturation of the data processing inequality for both quantities, if and only if we have exact recoverability for both quantities. However, now we can explore the approximate versions of both notions. And this is something that we can do using something that is called approximate data processing inequalities. We know that this quantity is always larger than or equal to 0 because of what we have said before. But of course, maybe there's a way to provide lower bounds for this quantity in terms of the distance between a state and its recovery, instead of the best, in terms of the best recovery maps applied to the channel, applied to the state. And this is something that has been explored by many, many people in the literature in the past few years. And in particular here, I wanted to highlight this result of Carlin and Berchinina, which is providing this lower bound for this quantity, because it actually gives you a difference between the state and the usual PET recovery map, which is the one that I was listing before. All the other results involve other quantities that are rotated PET recovery maps and these things. So here what you see is that we know that we have an exact recovery if and only if we have an exact saturation of the data processing inequality. But here, this is also telling us that if this quantity is small, then in particular, we are close to the recovery of this state. However, I must say that I'm kind of cheating there because all these prefactors are pretty large in principle. So even if we have an approximate recovery, I think you should take this with a grain of salt, no? Because you are paying a big price here. But this is something that you can also explore in the BS entropy framework, and you obtain something that is very similar. So the prefactors you see that are actually pretty similar to the ones here. And we also have the difference between the state being recovered and the BS recovery of the state. Here I wrote it in terms of sigma, but we see that recovering sigma, so sigma being close to being recovered by the BS recovery is equivalent to rho being recovered by the BS recovered applied in rho, and now defined with respect to sigma. So there you have a symmetry between all these, between these two different definitions. So this is totally fine as well. So this is something that is usually called a strengthened data processing inequality, because again, this is strengthening the zero bound that we know that we have for both quantities. But if we really want to have an equivalence here, this is only giving us one direction in these arrows. If we really want to have an equivalence, what we want to have is also an upper bound for this quantity in terms of something that gives us the distance between rho and the recovery of rho by this expression. And unfortunately, this is unknown. So there's no result for the relative entropy in this direction that gives us the distance between rho and its PET's recovery. So this is an open question that I leave here in case anyone is interested in this. And what happens now for the BS entropy is that very funnily, even if it seems that it's a less interesting quantity because of the recovery being not a quantum channel and all these things, it's actually easier to work with sometimes. And in particular, what we see is that we can really provide an upper bound here that we cannot provide for the relative entropy. And well, the bound, I won't say that it's beautiful because it's not, but it's really something like this, no? So it's something that gives you an upper bound for this difference in terms of, this is the important part. So this is the product between the state rho and the inverse of the BS recovery. So now I took actually the inverse and the adjoint, but okay, we have equality if and only if we have equality with the adjoints. So that's also something that we can take. And well, in particular, this is stronger than having the difference between rho minus this term here, right? Because we would extract it, no, the other way around, it's weaker than having this. So this is a quantity that is larger than having the difference between this and this without the inverse in one norm. And to achieve this, we have a lot of prefactors, which are also a bit problematic sometimes, but at least we don't have fourth powers or these things as we had in the lower bound before. And this is something that is not very readable, but maybe for simplicity, if instead of taking a usual quantum channel, we take a conditional expectation, which you can think of as a partial trace. So just imagine that a conditional expectation is a partial trace normalized. Then in that case, what we have is that we have equality in the data processing inequality to 0, if and only if the state, for example, sigma in this case, is recovered by the state rho utilizing this expression here. So rho, E of rho minus 1, and then E of sigma. So this is how we can define this B E of rho of sigma. So this recovery condition, this BS recovery condition. And then what this is showing is that this difference is upper bounded by terms depending on rho, sigma, and the channel. So in particular, on this conditional expectation. And then the infinity norm of the difference between the product of the state and the inverse of the BS recovery. Well, we can do that for both of them, both for the rho and both for the sigma minus identity. So this is what this is essentially telling you. And the proof, as I mentioned before for the other result, is also based on the integral expression for the matrix logarithm. So it's really, this is the magic behind the proof, just writing these things with logarithms and simplifying terms, and then using multiple norm inequalities. So there's nothing else behind that. So with this, what we can actually do is rewrite the expression that I had before, and I really simplified it now to the conditional expectation case, because with the channels it's a bit too messy. And this is what you obtain. So you obtain now an upper or lower bound for the difference between these BS entropies in terms of the distance from the state to be recovered by the BS recovery. So this is why now you really have approximate recoverability if and only if you have an approximate data processing inequality in a sense. So both a strengthened and a reverse data processing inequality. Okay, but now what we can do again is look at this simplified case because it's a bit nicer and a bit easier to understand. And this is what I introduced before, right? So how I introduced this conditional mutual information in this tripartite space framework, and how this can be reduced to the BS conditional mutual information also in this tripartite framework. And these are the notions that we defined before. So what we can do is explore the same question exactly in this framework here. And this is essentially coming from here, no? So from the fact that we have the CMI vanishing if and only if we have this expression for rho, and we have the BS CMIs vanishing if and only if we have this asymmetric expression for rho. Again, I'm missing the -1 here. So do we have approximate versions now for these inequalities? So approximate versions for these conditions, for these equivalencies in this particular framework that are a bit nicer than what we can obtain from here? And the answer is yes. And finally, in that case, there is really an upper bound for the conditional mutual information. So this part that we didn't have for the relative entropy, we actually do have it for the conditional mutual information for this particular case. And if you want an intuition why this can be proven in this case and not for the relative entropy case, this is coming from a continuity bound on the conditional entropy. Because the conditional mutual information can be written as the difference of two conditional entropies, and now you can apply a continuity bound on the conditional entropy to upper bound this quantity in terms of the distance between these states where these conditional entropies are defined. And this is something that can be refined after applying a channel, and the channel is essentially the PETS recovery. So this is why you can prove this upper bound that in general you cannot prove for whenever you have here a difference between relative entropies. And the lower bound is just a way of rewriting the lower bound that we had before. So this doesn't change at all. And here for the right side, we have exactly the straightforward identification of the result that we had on the previous slide, but now for this particular setting of the tripartite Hilbert space. So it's a bit messy, but the idea is exactly the same thing that we were saying before, is having an approximate version of these equivalent arrows that we have here. So I know it's a bit too messy, but just take what I'm trying to say here, not really the expressions in particular.
Okay, so could you just show us very briefly that slide again where you didn't have the inequality for the general case, but you knew it for the Belevkin-Stashevsky, right? Like you had two and you said a question mark, I think it was. This is what you were referring to, right?
Yes.
Like that you couldn't get an answer on the left-hand side, but you were able to using the Belevkin-Stashevsky.
Exactly.
Okay.
So
Okay.
Here we actually had this question mark, and here we don't. And in the tripartite Hilbert space case, we don't have this question mark anymore. Of course, this doesn't mean.
Sorry, I meant to ask, what is when you write this approximate equality, what was the measure you used to say like these two states were related to each other? Was it the norm one?
That's a very good question. So the fact that I'm writing it in this sloppy way is actually on purpose because all these people use different measures. So it's a bit complicated to say here. I like the one norm because, well, the one norm is very easy to implement and it's the kind of canonical way to measure distance between the states. But actually, the first results that appeared measuring this distance that are due to Fossey and Renner, this was done in terms of the log of the fidelity between both states. So it was going like in the opposite direction. The fidelity is telling you when two states are very alike, the fidelity is larger. And so as the opposite to the relative entropy or to the one norm of the difference between the states. No, so but this is for them it was better to work with the log of the fidelity. And here there are also some people that use a measured relative entropy for as a figure of merit to measure how different these two states are. So this is why I wanted to write this approximate, and there I leave some space, no? So to see which measure is better for you.
Thank you. That was very helpful.
Thanks. So what happens now is that we can use these expressions to get some applications in mathematical physics. And I don't know if I want to do this or I actually want to skip this and talk a bit more about Rényi divergences because I'm not going to have time. So what I'm going to do is skip this. And if anybody is interested, we can talk about that later because this would make me have to introduce Hamiltonians because this is essentially telling us how to apply the results that we had before in the context of Hamiltonians and in the context of decay of correlations of Gibbs states in 1D and then seeing Gibbs state learning and all these things. So we can discuss this offline if anybody's interested. What I will do is use the expressions that we had before to introduce something that I think is a bit more interesting for this community. And it's something that is called quantum Markov chains and approximate quantum Markov chains and BS quantum Markov chains and all these things. And what we do to introduce these quantities is again look at the particular case in which we have tripartite spaces. So now again we have three systems A, B, and C, and we look at the conditional mutual information again, and we have again that the conditional mutual information vanishes if and only if we have this expression. And I didn't give it a name before, but this is what is usually called a quantum Markov chain. So you have a state rho ABC written in this form, if and only if this is a quantum Markov chain, or well, actually the definition is coming from this. So you say that a state is a quantum Markov chain, if and only if its conditional mutual information is zero. And these states are very interesting for many different reasons, but in particular, because they represent Gibbs states of local commuting Hamiltonians. And that means that, therefore, studying them is very useful when you are trying to do some applications in the many-body context. And of course, I've been talking about the BS entropy all along. So what I want to do is study something similar in the Belafkin-Stachewski case. And we want to see what happens when we have this expression. Again, sorry, I'm missing the -1 here. So what we want to do is see what happens when we have this expression and how we can define states that satisfy these equality conditions. And this is something that we call a Belafkin-Stachewski quantum Markov chain. I mean, the name is not tremendously original, but you will see that it has very interesting properties that don't have anything to do with the quantum Markov chains. So the first thing that I should say is that, well, they are, again, easier to construct because of the lack of square roots. And
Can I ask a quick question?
Yes.
So usually like in like classical stochastic processes, when one speaks of like three random variables forming a Markov chain, right? There's a sort of like temporal order
Yes.
Within the variables, right? And there's like, you know, so the so the state at one time only depends on the state at the previous time or something like that, right?
Yes.
So how do you think of when you have like a tripartite state where there's no temporal, when there's no like a priori ordering between the systems, like how do you think of that as like what's the reasoning behind thinking of some sort of like analog of a Markov chain in that case?
That's a very good question. Indeed. I mean, if we are calling this a quantum Markov chain, it has to do because it has something to do with classical Markov chains, right? So I totally agree with you. So the idea is a little bit like that. You are imagining that you are going from A to Z. So temporally, you are really having something that goes from A to Z in a sense, if you want. And what is happening here is that you have a quantum Markov chain between A and C condition to be, if and only if this condition happens. So you have the CMI being equal to 0. And because of the definition of the CMI in terms of the von Neumann entropies, you can actually see that this is reversible. So if you see C as the future, A as the past, and B as the present, it's actually the same in this case as seeing it the other way around, as A as the future, C as the past, and B as the present. And but it's just because of how it's defined here. But what happens as well is that if you now have a system that is A, B, C, D, and you have a quantum Markov chain between A, B, and C, and another one between B, C, and D, and they are compatible in B and C, you can merge them. You can like put them together, and then you can create a larger quantum Markov chain between A, B, C, and D. So this is also something that is reflecting what happens in the classical case, right? So this is why now what you can actually see is that you have somehow exactly what you are saying, no? So a larger quantum Markov chain, if you want, if you merge many of them, that goes from A, B, C, D, and so on and so forth. So if you really construct like a temporal line in that direction, this really mimics this classical behavior.
Okay.
Okay, great, thanks. So this is what happens in this case. Now, when I introduce this Belashkin-Stashevsky quantum Markov chain, this is a bit more convoluted because what is happening again of being able to merge things is still happening here. However, here the time only goes in one direction. So here, if you have, even if I'm writing here this quantity between A and C condition to be, what is actually happening is that this is not reversible between A and C. This is not symmetric, sorry, between A and C. So the expression that you have here, if you invert the roles of A and C, this is giving you something that is totally different. So even if they still vanish in the same state, so you will still have exactly the same expression here, the quantities themselves are totally different. So you cannot really have exactly the same knowledge that we were saying before. So here is a bit more convoluted in that sense, but it has nicer applications for some other reasons. So again, what we were doing is exploring this. Sorry, the -1 is missing everywhere, so it should be here as well. So what we are doing is exploring how we can relate quantum Markov chains and BS quantum Markov chains. And for that, what we do is look at the general case. So we look at the cases in which we have saturation of the DPI for the relative entropy, and the cases in which we have saturation of the DPI for the BS entropy. And we try to compare these recovery conditions. So when do we have one and we don't have the other, and the other way around? And what we can actually see is that if we have this, then we always have this. So if we can recover rho by the PETS recovery map, we can always recover it by the BS recovery map. However, the converse is false. So there are cases in which you can recover with the BS recovery condition and you cannot recover with the PETS recovery map, which means in particular that if you take the difference between this quantity and, well, this and this, and this and this, then the kernel of the difference of this quantity is contained in the kernel of the difference of this quantity, but not the other way around. So when you actually explore the kernel of the quantum Markov chains, the kernel of the conditional mutual information, it is contained in the kernel of all these BS quantum conditional mutual informations, but not the other way around. And what we can see, I mean, it's very easy to construct counterexamples. So it's very easy to construct states for which you have this and you don't have this. So numerically, we have some examples here, but it's really very easy to do. So this is a way to say that the states, the set of states that are BS quantum Markov chains is larger than the set of quantum Markov chains, but this doesn't really give us any information of how much larger or what can we do with the BS quantum Markov chains that we cannot do with quantum Markov chains or anything of the sort. So what we did in this recent paper is explore this a little bit better. And this is now a bit too technical, so I don't want to go into many details here. But what I want to say is that there is a relation between having a state rho ABC that is a BS quantum Markov chain and having a state eta that is a quantum Markov chain. So what you do is you start with a state, with a tripartite state rho ABC, and you construct a state eta ABC from it in the following form. So you take rho ABC and you conjugate it with rho b minus 1/2, rho b minus 1/2, and then you divide by the 1 over the dimension of the B part of the system. So that's now, this is also a density matrix. So this is just so that this is a density matrix. And then what happens is that you have created from any state another state that is totally associated to it, right? Because there's a relation, well, a direct relation between these two states. And then what we can show is that this rho is a BS quantum Markov chain if and only if eta is a quantum Markov chain. Which means now that you can go from BS quantum Markov chains to quantum Markov chains and the other way around very easily. So now you, every time that you have a BS quantum Markov chain, even if this state is not directly a quantum Markov chain, you can construct another one from it. This is essentially the idea of it. And what is very, very interesting in the case of quantum Markov chains is that there is a way to decompose the Hilbert space of the middle system, of the B part, such that you can write your state rho, in this case eta ABC, as a direct sum of tensor products between A and a B and a part of B, then tensor, the other part of B and C, and then a direct sum of all these things. And this is something that, because of having eta now being a quantum Markov chain, we can actually do for rho. So for the BS quantum Markov chain, we can write it in this expression that I have here. So we can write it as rho B1/2 and rho B1/2, and some unitaries here, and this direct sum of tensor products of density matrices that are defined in A and some part of B, and B and some part of C, with the corresponding weights that you have to put so that this whole thing is a density matrix. So this is, well, this is a bit complicated to grasp in a few minutes, but this has very interesting applications, and it's the reason that I wanted to mention it here. Let me just first say that all that I just said, I said it for tripartite spaces, but you can extend it to quantum channels, arbitrary Hilbert spaces, H and K that are finite dimensional, and so on and so forth. So this is too technical, but just to say that this can be done. And coming back again to the tripartite Hilbert space case, what this is telling us in particular is that now we have equivalence between the conditional mutual information of rho being equals to 0 to the VS conditional mutual information of eta being equal to 0. So now you really have an equivalence between the two quantities. And the reason why this is so interesting is something that I skipped that I was supposed to say before, but maybe in just saying it in 2 lines. What happens when you have a BS conditional mutual information of a one-dimensional Gibbs state is that you can see that if now A, B, and C have some physical meaning, so if they are a quantum Markov chain, if they are a spin chain, and A and C are separated and B is the system in the middle, then this quantity actually decays super exponentially with the middle distance, so with the size of B. And this is very interesting because this is a behavior that is not observed for the conditional mutual information. So this is something that cannot be, well, with the current techniques in the literature, it cannot be proven for the conditional mutual information. So it means that if you want to measure conditional independence in spin systems, this is a quantity that is giving you some information that this quantity is not giving you. So this is why now it's very interesting to be able to go from one to the other and the other way around. And also, this is telling you that if you want to do, in particular, if you want to do MPO approximations of Gibbs states, so this is the application that I had before that I didn't mention, but also for many other applications, there is a map that you can construct that is much more interesting than the map that I had before, which is this map here. And this map is very convoluted. So what you are doing is taking the rho BC and conjugating it with the rho B minus 1/2 on both sides. And then you're also conjugating it with this term here and this term here, which are the same, and then rho B 1/2 and rho B 1/2. So this seems a bit arbitrary at the moment, but actually it's not. And the nice thing of this map is that this is linear with respect to the state that you put here, or with respect to the observable that you put here, and it's completely positive. So now this is definitely not trace preserving, but this is a map that is linear and completely positive with respect to the input that you put here. So what this is telling you is that the BS conditional mutual information vanishing is equivalent to a recovery condition that is linear and trace preserving, but not positive, and is equivalent to a condition that is linear and completely positive, but not trace preserving. Of course, you cannot have both things at the same time, because one thing that Pets proved many years ago is that you have a recovery for the relative entropy. So in particular, you have the usual CMI being equals to 0, if and only if you can recover your state, in this case, from B to C. This is what this map is doing. So you can recover your state from B to C by any completely positive and trace-preserving linear map. And then, in particular, he showed the thing that now we call the PETS recovery map. But he showed that all these maps that are called recovery map per se, which are the completely positive trace-preserving linear maps, are equivalent. What this is telling us is that none of these maps can ever be linear, completely positive, and trace-preserving, because otherwise we will have the same recovery conditions as the usual CMI, which we know that is not true in general, because we know that the recovery for the BS has to give you a larger set of states than the recovery for the relative entropy. So I know that this was a bit confusing, but I hope that it convinced you that this is more or less reasonable, why this has to be in this form. And well, what I will do is conclude by mentioning a little bit of what happens with other divergence measures. I just talked about data processing inequalities and quantum Markov chains and analogs of quantum Markov chains for BS entropies and all these things. But if you remember at the beginning, I was also talking about...
Before further going on, I
Yeah.
have a question regarding the slides before you present the theorem.
Yes.
Maybe like some slide, yeah, here. So here it seems so like you said that if PETS recovery map works, then this BS recovery map works, but not the other way around, right?
Yes.
So what do you mean by that it doesn't work? So like does it works approximately, or like
Not
so like
necessarily
because
as
like
well.
I was a bit confused because I thought PETS recovery map is a pretty good decoder. So whenever there is some best decoder exists with some error epsilon, then PETS recovery map should also work with like twice so small error. But
Yeah.
like so
So-
doesn't it contradict to what you write here?
So isn't it a problem exactly what I'm saying, that this map is not completely positive?
Okay.
Because I think this is where the catch is, right? Because I agree with you that if you are only recovering with quantum channels, then definitely the PETS is the best one.
Yeah.
But here, what I'm calling recovery is kind of cheating a bit, not because of what I'm saying, because this is not a completely positive map.
Oh, okay. Yeah, that makes sense. Thanks.
Thank you. Yeah, this is why, again, all these quantities and all these notions, I think, are very useful for other purposes, like really more for applications in many body and these things. But for the specific implementation of things related to quantum information, is maybe a bit more problematic because of none of them being really a quantum channel. Okay, so let's move to the last part. I will very, very briefly mention what happens with other divergence measures, because at the beginning we also had range divergences. And again, here we have the problem that we can define them, we can extend them to the quantum world in many different ways. So we can, for example, by taking this expression and taking the straightforward definition, if you just map these probability distributions to states, we have the straightforward definition that is given by the best range divergences, which is given by this expression that is right here. If we want to symmetrize this, so that, well, actually this is coming from taking the minimal possible divergence that actually reduces to this quantity when taking diagonal matrices, then you obtain something that is called sandwich range divergences, which is given by this expression here. And you can also extend it to something that is called geometric range divergences, which is defined by this expression here, and this is coming from some geometric means. So it's not an arbitrary definition, again, it's coming from something that is very reasonable. And what happened when we introduced the range divergences was that when we took limit with alpha going to 1, we always recover the Kullback-Leibler divergence. But now we know that in the quantum case, we have introduced both the omega-k relative entropy and the BS relative entropy. So what do we extend with these quantities? And what we can see is that the PETS and the sandwich, both of them extend the omega-k relative entropy, and the geometric range divergences extend the BS relative entropy. So again, if you prove things for both the PETS or the sandwich, you can, by taking the limit, obtain things for the omega-k. And if you prove things for the geometric range divergences, taking the limit, you can obtain the same things for the BS entropies. And maybe to give you an intuition of what happens with these quantities, I took this picture from a paper of Fan and Fossey, in which they show that for these specific matrices, if you plot all of them, they behave in this form. This is the relative entropy, and this is the BS entropy. So we know always that the BS entropy is an upper bound for the relative entropy. And what happens now, if we take the limit, the curve, sorry, of geometric range divergences between 1 and 2, it's this line that we are plotting here in blue. And if we take the sandwich range divergences, this is somehow a parallel curve to that one. So this is this orange curve that is kind of parallel to the blue one. And in a sense, the best range divergences are something that interpolate between this value, so with the relative entropy in when alpha tends to 1, and funnily enough, when alpha equals 2 exactly, the best range divergence coincides with the geometric range divergence. So it's this green line that kind of interpolates between sandwich and geometric range divergences in a sense. We can, of course, ask as well what happens with data processing inequalities for quantum range divergences. If we can prove, well, in general, they all satisfy data processing inequalities. So this is why we consider them to be acceptable definitions of range divergences or divergences in general. And there are multiple results of strengthened DPIs for PETs and sandwich range divergences. So strengthened DPIs, again, are the lower bounds for the relative entropy, for the difference between the range divergences in terms of the distance to the corresponding recoveries. Now the recoveries are different for each of these quantities, so this is something that one has to be careful with. But there are many different results, and if you want to get like a good summary of many of these results, I recommend this paper because this paper contains a lot of these inequalities. And here I just want to show one particular result that we have for sandwich range divergences, not for the others. And the reason why I want to show it is because we actually have both the lower and the upper bound. So what we do is define the sandwich range CMI, so the sandwich range conditional mutual information, as the difference of two conditional mutual range entropies in this form. So each of them is just like the usual sandwich range divergence. But now sigma depends on rho again. So this is taking as something like this. And what we do now is take the difference between these two terms and defining the sandwich range CMI as the difference of these two terms. We can show this lower bound, which is something that is actually extracted from the paper that I just mentioned in the previous slide. This is very convoluted, so it's not very important to understand exactly what it says with the constant and everything. But the important thing is that here we can only put something that is a rotated PETS recovery map, not really the PETS recovery map itself, because if you see here, you have a plus IT and minus IT everywhere. So you have this rotated version. And here, as the upper bound, we can actually put the difference between the state and the PETS recovery map. I believe that the fact that you really need here the rotated version is an artifact of the proof rather than something that is necessary. But well, this hasn't been worked out yet. So it's also a possible open problem. Try to find a lower bound for this quantity in terms of a recovery map that is really the usual PETS recovery map. And this is something that we could prove for alpha between 1/2 and 1. And also we could prove something very, very similar for alpha between 1 and infinity. So for all sandwich range divergences in general. With this is the last thing that I wanted to mention. So with this, I will conclude. What we have done has been essentially to review entropies and divergence measures that have appeared in classical and quantum information theory. And we have reviewed some results of strengthened and reverse data processing inequalities, and we have seen how this relates to approximate recoverability of states. And the important particular case that we have also reviewed has been that of tripartite Hilbert spaces. What we have used, what we haven't done is that the application of these results to the study of decay of correlations and learning of Gibbs states. So this is something we can discuss if you want. And finally, in the last part, we have very briefly talked about quantum Markov chains and introduced the analogous notions for the BS entropy. And we have very, very briefly now recalled some quantum range divergences and seeing how you can also prove data processing inequalities for them and what this actually means. So with this, I conclude what I wanted to tell you about, and I thank you very much for your attention and for your questions.
Thank you very much, Angela, for this superb presentation. I really enjoyed that. Thank you very much. So if there are further questions, we might be able to take those. Yes, please.
Yes, I have some question on the slide of family divergences. I wonder, so yeah, like can you go to the next slide maybe? But like here is actually like, okay, yeah. So like I see that for geometric Renyi divergences, alpha takes a value between 1 and 2. But
Yes.
like, what is the obstacle when you try to extend to alpha less than 1?
That's a good
Is
question.
there, yeah, like, because like, yeah, like if I want to compare these three relative entropies on the top to the bottom one, especially BS relative entropy and its Renyi extension, I wonder for, yeah, like,
Yes.
yeah.
I think actually between 1/2 and 1 is fine. It's just that, yeah, when I was extracting some of the results for, yeah, I think you can also do this here for between 1/2 and 1, if I remember correctly. I was extracting some of the results from this paper of Fan and Fossey, but I think they also do it for between 1/2 and 1. I mean, beyond 2 for sure not, because the problem is that beyond 2 you stop having a data processing inequality. So you can still define the quantity, but it's very useless, no? Because of not having a data processing inequality.
I see. Thank you.
Thanks, yeah.
Okay, so we have a question from Watanabe-san. Please go ahead.
Thank you for the talk. I had kind of a follow-up question about the naming of quantum Markov chains, because I guess your answer was somewhat like you're really focusing on one-dimensional, spatially one-dimensional systems, so that you can almost kind of regard that one dimension as the time direction. Am I right?
Yes, totally.
Okay, so in that sense, I guess this is like more related to those locally Markovian type of results rather than like if a dynamical system has a Markovian property, or are they actually related? I'm not an expert in this field. I only do classical Markov chains, so yeah, that like I'm wondering what exactly the connections are.
Yeah, I think it's a very good point what you are making there. So when we are talking about quantum Markov chains, indeed, the part chain is a bit misleading, because what is really what you should really infer from there is that we are having an idea of a 1D system, as you are saying. No, so it's really because this is the way that you are mimicking, in a sense, the line of the time. We are not talking at all about Markov processes, if you want. So this would be something that would be much more similar to quantum Markov semigroups in the quantum case. And as far as I know, I mean, there's a very convoluted relation that you can construct between both notions, but it's very far and it's in very particular cases. And what you can see is that if you have a quantum Markov chain that is governed by a Lindbladian, so something that is very particular. So it's not only governed by infinitesimal generator, but infinitesimal generator that satisfies the certain Lindblad form. And this is describing a dissipative process. Then sometimes, if you impose enough conditions, you can do it so that the equilibrium of the system is actually a quantum Markov chain in this sense, which is going to be the case in which you have a Gibbs state of a local commuting Hamiltonian.
I see.
So it's like a super particular case in which you can actually relate these two notions. But in more generality, as far as I know, there's no relation. It's just a coincidence, no, that both of them have this Markov in the name, I would say.
I see. Thank you. Sorry, one more thing. So can you extend this notion to like two-dimensional systems or higher dimensions?
Yeah,
I
so
mean,
actually,
sorry.
yes, sorry. So yes, actually, the quantum Markov chain, I mean, I just wrote it here in 1D because for simplicity, but it's usually used even more for high-dimensional systems, because what happens there is that you have, for example, a small region, call it A, and then some region around it, which is region B, and then C is the rest. And then a quantum Markov
Okay.
chain there would be exactly that, no? So scene A and scene C, condition 2B, which is the ring that separates them, something like that. And then what you usually do when you use this for Gibbs state, for example, is really that, is take a region, take the boundary of that region, which is this region where interactions are still supported, are touching your region still, and then take the complement of that, and then you see that if you have a Gibbs state of a local commuting Hamiltonian there, then this is actually equivalent to having a quantum Markov chain there. I mean, in that case, it's still called quantum Markov chain, which is a bit misleading, but sometimes people just call it quantum Markov state, so that is not so misleading, no? So that's
I see, yeah.
the 1D there.
I see. That does sound less confusing, but okay, thank
It
you.
makes more sense, yeah. You're totally right. Yes, thanks.
So I guess what you're saying is that you can always just consider a spherical coordinate or something, and then in that case, the radius direction is always one-dimensional, so you can kind of do that kind of thing. At least in the first example, like if you have one region and then another region just that's surrounding it, it's almost like that, right?
In a sense, yes, but it's not really necessary. So when you are only working with quantum information, you don't really have that geometry in your mind. No? So sometimes it's not really so important what the shape of the regions has.
Okay.
But even for spin systems, sometimes you just have like square regions, or you just have regions with a weird geometry. And then the only thing is that you have like some fattening of the region around it, which is this, like a ball that you put around the region, but it doesn't need to be spherical. No? And you still have exactly the same behavior, because the only thing that you care about is the interactions that touch your system, that touch this smaller region that you're considering.
Okay, I see. Thank you so much.
Okay, thanks.
Arthur?
Yeah, thank you. I really enjoyed this talk, and I have a lot of questions, but I think one of them is the most important, which is earlier in the talk, you introduced the whole family of divergences that you said a recent paper showed how you can like have this whole parameter family, and then you also compared then you focused primarily on just these two entropies, the Levkin-Stashevsky and the Umegaki, and you had a bunch of theorems that said sometimes we have bounds here, sometimes we don't. In the case of conditional mutual information, we do. And you also wrote down like recovery maps for each of them. I'm just curious why you kept them separate. And maybe that paper is so new that like it hasn't yet been analyzed, because you have this whole parametrized family. So I would have expected, right, like maybe there's a way to connect between the two by looking at the recovery maps associated for each of them and things like that. Do you have any comments on this?
That's a really, really good point. So this paper, when we found it, so the problem of the paper is that the idea is very good. So it's really like some sort of interpolation between these two quantities, right? But is okay. So maybe from our point of view, it's maybe not very easy to really work with these quantities once they are defined in these forms, because they are not extremely explicit in a sense. No? So it's very difficult to prove all these things that you're saying. So what we are actually doing now is a current ongoing work with some collaborators is something very similar to that. So we are defining another kind of interpolation between these two quantities that is much more explicit and is very easy to see. So you can really write it down. And we're exactly doing what you are saying. So we are really defining recovery maps for each of the points of the path. And we are defining the associated quantum Markov states, in this case, associated to each of these parameters. So we are seeing these two extremal cases, exactly as you are saying. No? So the relative entropy and the with the corresponding quantum Markov chains that we know that both of them have now separated. And now we are sort of interpolating between them, creating all these recovery maps that happen along the way, and seeing how you can reduce from to one and to the other. So yeah, it's a very, very good intuition, yes.
Okay. Interesting, thank you. We should maybe talk about this.
Okay,
Thanks.
perfect. Thanks a lot.
James? Yeah, go ahead.
Sorry, I hadn't unmuted myself. Yeah, I was just going to mention something in the direction of what Arthur was saying, because we have a paper where we actually define like a parametric family of recovery maps as well. So it would be
nice.
interesting. I mean, just as a comment, right? Just to see if the parametric family of recovery maps we define are related to yours or the one in the other paper or something like that as well.
Okay, thanks a lot for the comment, because I didn't know that. Then I should definitely check that, and we should definitely talk, yes. Yeah, right now I don't know, but thanks a lot. Yes, I should check.
Yeah, actually, the two recovery maps, the PETS map and the other one called B are two special cases of the recovery maps defined in our paper as well. Yeah, so
I
there's
see.
probably a connection there. Yeah.
So then there's probably a connection. Okay, I see.
Yeah.
Okay, then thanks a lot for telling me. Yes.
So lastly, I also have a question, or well, an observation, that linking the drop in relative entropy to recoverability might be missing part of the story, because classically you have something that is much, much stronger than that. Classically, when you have everything, just classical probability distributions and classical channels, the drop of Kullback-Leibler divergence is actually equal to the relative entropy between now two processes. So like two joint distributions. The first joint distribution is taken by having, as the input your initial state, and as the channel, the usual channel, the forward channel. The other joint distribution instead is constructed by having is a reverse channel, is a reverse process that has as input the final state of your initial state, and as the reverse channel, the Bayesian inverse constructed with respect to the prior. So classically, you have an equality, and then you have the recoverability theorem just by monotonicity of Kullback-Leibler divergence, just by tracing over the output alphabet. Okay, so I know, it is already so hard to just generalize the inequality with respect to recoverability. But classically, I would say that this is a crucial point conceptually, because it relates the drop in relative entropy with the distinguishability of two processes, a forward process and a reverse process. And this notion of distinguishability or statistical comparison between forward process and reverse process is at the basis of all these fluctuation relations in statistical mechanics. And this is how you get the second law out of these things. So do we have any, and we have something about Belafkin-Staszewski relative entropy where you can actually, where you have an equality somehow between the drop of Belafkin-Staszewski relative entropy and a kind of a 2-point process on the other side. Do you know anything beyond that? Have you ever investigated this?
Well, I haven't, but if I'm understanding correctly, I think quantumly, at least for the relative entropy case, there will be a problem for that. Because if you, well, this is for the general case, no? But even if you look at the, even if you look at the particular case here, oh, well, that's fine, I guess. Sorry. So even if you look at the particular case here in which you have the tripartite space, right? So even if you have the CMI and here being recovered to the usual PETS recovery map with the product of the marginals, there's this paper from Suter and Renner, and I think before there was a paper from Andreas Winter with some co-authors, in which they actually showed that you cannot really have this equivalence without bringing a p-factor that depends on the dimension of the system. And it's not very difficult to see, that if you construct a strengthened DPI even for the conditional mutual information, but having an upper bound in terms of the distance between the raw and the recovery, you have to pay a prefactor. So this is actually for them. If you see how they phrase it in that paper, they phrase it in the totally opposite direction to what I'm saying here. So they don't say you have equivalence between these two quantities, but the other way around. They say you can never have equivalence because, okay, as I was saying, these epsilons, I'm cheating a lot. These epsilons can be huge, So because you're paying these dimensional prefactors.
About the recoverability, right?
Sorry?
This would again be about the recoverability part. What I'm saying is that you would really have like a joint process.
Yes.
Okay, but maybe one day we will have to discuss this more in detail. But,
definitely, yes. but exactly what you were saying, I wouldn't know how to do that, to be honest, because of course I see classically how you can write this as one unique expression, right? As one unique Kullback-Leibler divergence. Quantumly.
Yeah, what we have in fact is with the BS entropy.
Yeah.
So also in this case, it seems that somehow there are some situations in which BS entropy is the analog of Kullback-Leibler divergence rather than Umegaki relative entropy, but not always, of course. Yes.
I would be very happy with that, yeah. Because I particularly like the quantity for the other applications. No, but yeah, I totally understand. Yeah. I don't know if you can do something like that for the relative entropy, but at least we have never explored something like that for either of the quantities. But thanks a lot for the comment, yes.
Thank you, Angela. Okay, I think we are ready to close this meeting.